You've probably heard of partial derivatives somewhere if you're a physics or math student. You might have seen this notation, these equations, or this absolute demon, which I keep seeing everywhere for some reason. But now we finally get to learn and understand what these partial derivatives are in a simply mathematical context. Again, as we did in the previous video on introducing functions of multiple variables, let's start with a familiar single variable case and then move on to its analogous multivariable case. We hear the derivative being described as the rate of change of a function many times, but what does this actually mean? Well, we can visualize it here on a graph with input variable x and output variable y. I'll briefly explain derivatives in single variable and then we can move on to the multivariable case. Basically, to make this very short, because I'm sure everyone knows what a derivative is after AP Calculus Bootcamp.
Look! Away from me!
It's how sensitive the function is to changes in x. With every small step of delta x, this flat graph, which is y equals square root of x, doesn't nearly change as much as this steeper graph, which is y equals e to the x. So we're just trying to see the ratio between taking small steps in x and the corresponding change in y that we get from making a change in x, which we can write as delta y over delta x. But this is just a slope formula for discrete points, if you'd remember. So to put it in terms of the continuous function, to get a function that denotes the slope at every point, we get the limit as delta x approaches 0 and get the notation dy dx, which should be very familiar, for very, very small infinitesimal changes in x. Now to bring this to the multivariable world, instead of dy dx signifying the rate of change of the function y with respect to x, we have partial derivatives. As you can see for 2D graphs with one input variable and one output variable, we get one singular derivative which explains the rate of change of the function with respect to the input variable. For 3D graphs with two input variables and one output variable, we get two partial derivatives. One derivative explains the rate of change of z with respect to x, where y is constant, and one derivative explains the rate of change of z with respect to y, where x is held constant. Partial derivatives only focus on motion in one direction. This can be easier explained with slices of 3D graphs. Taking the graph x squared plus y squared equals z, we can see that if we put a vertical plane for any constant y, we get a 2D slice of the 3D graph that is in a familiar parabolic shape. The graph of z is only changing due to x as y is frozen and held constant. There is no change or movement in the y direction. Similarly, if we slice the graph for a constant x value, there will only be movement in the yz plane. The x will always be that constant value, and thus, since there are only two variables in action, you get a 2D slice of the 3D graph. So now let me explain how to compute the partial derivative so that we can paint a better picture as to what we're actually doing here. It is as explained before, one of the input variables is treated as a constant. So for the previous example, x squared plus y squared equals z, we can see that if we take the partial derivative of z with respect to x, we only want to focus on movement in the x direction and we want y to be a constant. So our partial derivative with respect to x is going to be 2x. If you wanted the partial derivative with respect to y, treat x as a constant and differentiate y squared into 2y. In this specific case, for any constant y, the partial derivative of the graph is always just going to depend on x, since it is 2x and vice versa. For any y equals constant c, the partial derivative is 2x depending only on the x direction. If y equals 1, you get 2x. If y equals 2, you get 2x, and so on, since there is no y term in the derivative. Since every y equals c slice you take, you'll end up with the same partial derivative. Just to note, some graphs instead, for different values of the constant y, we get different partial derivatives, making the xz graph either less or more steep, so the slice isn't going to look the same for every constant you choose. This happens when the partial derivative with respect to x still has at least one y term in it. Not that important, just shows that graphs can get a little bit more complicated. Now let's evaluate partial derivatives at a point. We will analyze the function x squared times y plus y to the third power plus x squared. If we take a slice holding y constant at y equals 1, for example, we will get a 2D graph that changes only on the xz plane. Now let's replace all of the y's in the function with 1 for simplicity. Now we get x squared plus 1 plus x squared equals 2x squared plus 1. Now, the partial derivative is just the derivative with respect to x, which is 4x. If we wanted to evaluate it at, say, point -1, 1, the partial derivative is 4 times -1, which is -4. So the slope of the tangent line of the slice in the plane y equals constant 1 at x equals -1 is -4. To take the partial with respect to y, let's hold x at a constant 2. So we can replace any x in the function with 2, making it 4y plus y to the third plus 4, and differentiating with respect to y, we have 4 plus 3y squared. Now if we wanted to evaluate it at point 2, 3, we plug in 3 for y in the partial derivative, and see that the slope of the tangent line of the slice in the plane x equals 2 is equal to 4 plus 3 times 3 squared equals 4 plus 27 equals 31. Now I'd like to introduce an approximation formula that uses partial derivatives. Recall how in single variable calculus, there were tangent line approximations in which we could approximate a function near a certain point using its tangent line at that point, since the tangent line and the function are very close to each other for certain range of values. Of course, as we move further and further away from that starting point that we drew the tangent line with, the line deviates further from the graph. You can compute this tangent line if you're given a function and a point. If you have a function y equals x squared plus 2x plus 3, and you wanted to find the tangent line at point 0, 3, take the derivative, which is 2x plus 2, plug in the point, which you get 2, and now you have the slope of the tangent line at that point. Now the equation of the line itself, recall point slope form, y minus y1 equals m times x minus x1, where x1, y1 is the point you are given and m is the slope of the tangent line at that point. So plugging in, now we have y minus 3 equals 2 times x minus 0, so y equals 2x plus 3. As we can see on the graph, values very close to x equals 3 are very good approximations of the function. Near x equals 3, the tangent line is practically the same as the function. Not exactly, but for approximation purposes it works great. Analogous to the tangent line in 2D, in 3D graphs we have the tangent plane. Recall how in single variable, we have a tangent line that can be written in the form y equals mx plus b, which can also be written as y minus y1 equals m times x minus x1. In multivariable, the tangent plane takes on a similar form, except this time z is the output variable, and we need slopes in both the x and the y direction. Let's say we're given a point to evaluate the tangent plane at x1, y1, z1. So now we have something very similar to the tangent line, but expanded into the multivariable world. Z minus z1 equals a times x minus x1 plus b times y minus y1. I feel like this expression is slightly more illustrative if you move z1 to the other side, and I'll explain why. So first let me explain all the variables, as this looks like a lot to take in. A is the slope of the plane in the x direction, b is the slope of the plane in the y direction. So based on the definition of the partial derivative, this means a is the partial derivative of the function with respect to x at that point, and b is the partial derivative with respect to y at that point, x1, y1 plugged in. As for x1, y1, z1, remember, is the point we evaluated the tangent plane at. Also, keep in mind that z1 is the output of the function at x1, y1. So now, why do we have to set up this weird, confusing looking equation? Well, let's plug in the point x1, y1 into the tangent plane equation. You can see that the first two terms cancel out since they're being multiplied by 0, and now we have z1, which is exactly what we want. This ensures that the tangent plane goes through the point x1, y1, z1. Now let's just look at a specific example. I'm going to use the graph z equals 3x squared plus 6y squared plus 1. To get the equation of the tangent plane, let's choose an xy point and evaluate the z. If we wanted the tangent plane at point 1, 1, we see that plugging it into the function, the z value will be. So x1, y1, z1 is 1, 1, 10. Now the partial derivative with respect to x at the point is partial z over partial x equals 6x, and at the point 1, 1 is 6. And the partial derivative with respect to y is partial z over partial y, which is equal to 12y, at point 1, 1 is equal to 12. So our a and our b values equal 6 and 12 respectively. If we plug this into the tangent plane equation, z equals a times x minus x1 plus b times y minus y1 plus z1, we get z equals 6 times x minus 1 plus 12 times y minus 1 plus 10. Now looking at the math 3D, we can see that the plane comes very, very close to the actual graph itself. That's what makes it such a good approximation. This formula comes in handy when you have complicated functions that you would want a good approximation for the z value on. Alright, that'll be it for this video. Thanks everyone for watching, and as always, if you have doubts or questions, or if I made some mistake in the video, please leave a comment. The next one will be about second partial derivative test and optimization, so I'll see you there.